Hello and welcome to the next chapter in our adventure here. We're going to be talking about a couple things that are certainly related to the last chapter, but separated out a little bit. They're equilibrium type of things, but not quite, titrations and acids and bases and things like that. So they are shoveled out into their own little chapter, but they're very, very similar to what we just did, just with different subscripts. So we're going to be talking about solubility. And you talked about that in Chem 50 in your introductory chemistry class about how some things are soluble, some things aren't. We're going to kind of take that down and decide, is that really true? And it's not. Okay, and then we're going to talk about ion complexes, which are really cool things. Very similar to solubility, right? Solubility, we're making things like silver chloride. It sits as a solid at the bottom because it's not very soluble. Ion complexes, we're also making these complexes that involve a metal and some sort of ligand attached to it, but they're ions, so they stay in solution, but they also form often very strongly, as we will see in our work. So, solubility, you might remember seeing a table like this. It says, okay, if you've got salts that are made from lithium, sodium, potassium, ammonium, no matter what you pair with them, it's going to be soluble in water. But we know that that's not entirely true, right? Because you can't add an infinite amount of salt into water and have it dissolve. There is a limit to the solubility of salt in water. It's about 38 grams of salt for every 100 grams of water. So, yes, it's soluble, but there are limits to it. Things like nitrates and acetates are also considered to be very, very soluble, which means if you put a reasonable amount into water, it's going to dissolve and you're just going to have the separated ions. So for example, if I put sodium chloride or sodium nitrate into water, NaNO3 into a beaker of water, the only thing that's going to be in that beaker of water is some Na plus and some NO3 minus. They're not going to talk to each other. They're not going to be together anymore. That's kind of what soluble ions mean, soluble salts. We also know chloride, bromide, iodides generally soluble with the exceptions of lead, mercury, and silver. So we say, hey, if we tried to put some silver chloride, AgCl, solid into water, pretty much what you learned in Chem 50 or in introductory chemistry was that AgCl would just sink to the bottom and be a little pile of solid silver chloride on the bottom. And what we're going to break down in this chapter, is that really true? Is it really true that not a single molecule, I mean, remember, if you got a pile of it here, you're talking about 10 to the 20th, 10 to the 30th, I mean, probably not 30th, but 10 to the 20th, 10 to the 23rd, lots and lots of silver molecules. You think that not a one of them is going to dissolve? No, of course they will. I mean, that's just, you can't help it. One is going to dissolve. In fact, we can calculate exactly how much dissolves by using solubility product constants, which are equilibria involving solids dissociating into water. Great. But it's still good. This table is still useful because if you run across something on this table that's generally soluble, you know it's going to form those ions if you put it in reasonable amounts. And if you run across this table and you find something that's generally insoluble, you know that it's mostly going to form a solid on the bottom, but now you'll have a tool of calculating how much did actually dissolve. So that's what we're doing. I encourage you to be familiar with this table to be able to recognize especially lithium, sodium, potassium, ammonium, nitrate, and acetate as always soluble, and then the chlorides, bromides, iodides, and sulfates as generally soluble with a few exceptions. Know those exceptions. And then if you just guess that everything else is insoluble, you'll be right most of the time. So what are we going to do? We're going to actually calculate solubility. So let's take the one we just said. We're going to take some silver chloride and we're going to dissolve it in water. And we don't really need to tell you how much we have, because as long as we're putting in a visible amount, chances are most of it's just going to sink to the bottom and we're going to get an equilibrium. But you're like, Professor Clements, if you add more solid, shouldn't more go into solution, right? You just have more silver chloride. Shouldn't more go into solution? And well, what did we learn in our first chapter on equilibrium about the equilibrium expressions? What do solids do? Nothing, right? They don't affect your equilibrium expression. Why? Concentration's constant. To be more technical, it's because the activity coefficient of the solid is 1. But essentially, right, their concentration's constant. So as long as you have some solid, then whatever's in solution is the equilibrium amount in solution, whether it's a little bit of solid or a lot of solid. And that's a little bit hard to get your brain around, but it's true. I could have a grain of silver chloride in there. If I allow that to come to equilibrium, as long as I can still see some of that solid, I'm going to have the same concentration of silver ions in there as if I put in 500 pounds of silver chloride and I had the same amount of water on top. So a little bit difficult, but it's good to know that that's true. So what are we going to do? When we're talking about solubility, we're always talking about the solid dissolving into water. So we have Ag, aqueous, and Cl minus, aqueous. Let me fix my AQ there. Nobody ever accused me of having good handwriting. So that's what we're going to do. We're going to start off with an ice table. Why? Because we're doing equilibrium, and that's what we do. We do ice tables for equilibrium. What do we put in for our initial concentration of solid? We don't care! Right? Solids don't come into our equilibrium expression. So I usually just put a line there. You don't have to, but I usually just put a line there to remind myself that I don't care, and I don't need to sit there every line thinking, what do I put there? What do I put there? What do I put there? Just, and then it reminds me, I don't need to put anything there. How much silver do we have? None. How much chloride do we have? None. Right? We're assuming we're starting with pure water. How much is going to make? Well, stoichiometry tells us we're going to make x of that. We're going to make x of that. That's our change. 0 plus x, 0 plus x, we get that. And so we get our K expression here is going to be the concentration of silver times the concentration of chloride. And that's going to be equal to something we can look up. Now, these are not numbers you need to know. These are numbers you can look up in a table. And generally, a table is called a solubility product table. And so we can look that number up. It is 1.6 times 10 to the minus 10th. A very small K value, a very, very small K value, because not much dissociates. We say it's generally insoluble. Now, we had things like Kas and Kbs and things like that. And why did we put those subscripts there? It's because as soon as we put that subscript, we knew what kind of reaction we were talking about. So when we said Ka, we knew immediately that it was Ha dissociating into H plus and A minus, and no one had to tell us that reaction. It was just there built in. So we do the same thing here. Yes, this is a K, but we put a subscript on it, and we put the subscript Sp, which stands for solubility product, right? Product being the multiplication of things, solubility things dissolving, right? So look, we multiplied the things that dissolved, solubility product, okay. But that's what we call it, the solubility product constant. It's just K, that's all it is. But now by putting the Sp, we're saying it's a very specific reaction, which is the solid dissolving into ions. Well, we know how to solve that. X equals 1.6 times 10 to the minus 10th. So you get x squared is 1.6 times 10 to the minus 10th. You take the square root of that, and you get that x is 1.26 times 10 to the minus 5th molar. We look at our sig figs. We had 2 sig figs here, so it's probably reasonable to say that we have 2 sig figs here. 1.3 times 10 to the minus 5th molar. And so that x is the concentration of our silver, and it's also the concentration of our chloride ion, because our stoichiometry was 1 to 1 in this case. It's also what we call the solubility. And very specifically, very, very specifically, no matter what coefficients we had on these guys, let's say we had a salt that dissolved into 2 chlorides, or we had a salt that dissolved into 3 positive ions and 2 negative ions. X itself, just X when we solve, and you'll see some textbooks and some people online use capital S or lowercase s for this. I just used X for consistency because it's what we've used the entire time we've done solubility. Why introduce another new letter? So X in this case is defined as the solubility, even if you had, and I'm going to put these here and then erase them, a 2 here and a 3 here, where the X actually doesn't correspond to the concentration of anything, because the concentration you'd have to multiply by 2 to get the concentration of the first thing, 3 to get the concentration of the second thing. But whatever it is, we call X the solubility. But in those other cases, 2X would have been the concentration, 3X would have been the concentration, but X by itself, regardless of stoichiometry, is always the solubility. So when somebody says, what's the solubility of it? It's just literally whatever you solve for X. Have I said that enough times, that X is the solubility, that the solubility is X? Should I say it again? X is, okay. You get the point. So there we go, very simple example. Let's do a slightly more complicated example. Let's go for some lead 2 bromide, PbBr2. And we know, because we're going to be talking about a KSP value here, that it's going to be breaking apart into its constituent ions, F2Cl minus and lead 2 plus. And we can look up a KSP value for that, right? As soon as I write KSP, you know I'm looking at that kind of reaction. And the one I looked up is 1.4 times 10 to the minus 8th. Okay, so still very small. We're not going to expect much to dissolve. That's why we say that lead with bromide, chloride, iodine is generally insoluble. What does this look like? Ice table. We don't care about that one because it's a solid. We don't have any lead in our water, hopefully. I know there's lots of places in the world that do have lead in their water, but hopefully we do not have any lead in our water. So we put zeros there. We're going to make x of that. Oh, 2x of this one, right? Make sure you're getting those stoichiometric coefficients that we've practiced on equilibrium ice tables from the beginning, but they're really important here. And then we get x and 2x here. And we write our K value, specifically KSP, as 1.4 times 10 to the minus 8th. And that's going to be the concentration of lead 2 plus times the concentration of chloride squared. It's so easy to forget that square. So easy to forget that square. But you got to put that square there because, right, that's what the K expressions are. They are each thing raised to the power of its stoichiometric coefficient. We don't divide by anything because there's a solid on the left-hand side, so that's why there's nothing divided here. And so we just plug in those values. Again, just like we talked about when we first did these things, you have to plug that 2x inside the parentheses and square the whole thing, square the 2x, because the concentration is 2x. The concentration isn't x, and then we multiply it by 2. The concentration is 2x. So we put the 2x squared. We get 4x cubed is 1.4 times 10 to the minus 8th. We divide both sides by 4, take the cube root on your calculator, and you get that x is equal to 1.52 times 10 to the minus 3rd molar. That's what we call the solubility. So the solubility is 1.52 times 10 to the minus 3rd molar. Again, probably 2 sig figs, since we only had 2 sig figs in our KSP value. So 1.5 times 10 to the minus 3rd molar. Our concentration of lead is just x. And our concentration of chloride is 2x, which is 3.0 times 10 to the minus 3rd molar. So there's what we can get as the concentrations of our things. And again, x itself is the solubility. So if somebody said, what's the solubility of lead to chloride? I'd say it's 1.5 times 10 to the minus 3rd. If somebody said, what's the concentration of chloride in a solution with solid lead to chloride at equilibrium, very fancy sounding, I would say it's 3.0 times 10 to the minus 3rd molar. All right. We didn't have to make the small x assumption anywhere in there, so there was no small x's to check. Those were very simple equilibrium expressions to calculate, as long as you know how to do things like cube root and fourth root and stuff on your calculator. Your turn. What's the solubility of barium carbonate in water? There's the KSP value for barium carbonate, and you can go. We're back. Barium carbonate. First thing, here's a hint. Whenever I give you a name instead of a chemical formula, I'm testing you. I'm testing to see, do you know that in these things, what you really have to make sure you do is that you're writing down the correct ionic formula. Now, in this case, it's really simple because it does turn out to be just BaCO3. But what do you have to do? You really have to do the thing where you know the charge on barium is +2, you know the charge on carbonate is -2, and those combine in a 1-to-1, right? Because if I said barium fluoride, it would have been BaF2, since fluoride is just a -1 charge. So be aware of that I trick you on purpose, and I'm telling you that I trick you on purpose. When you've got that name there, you really have to make sure you're writing down the correct ionic formula, not just saying, oh, I've got barium, I've got this, done. You have to make sure your charges balance out. So we've got BaCO3 solid going to Ba2 plus and CO3 2 minus. We do our ice table. Looks like the ones we did on the last slide, pretty similar. 0, 0, x, 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 x. And so we get our KSP value of 2.58 times 10 to the minus 9th is equal to the concentration of Ba2 plus, the concentration of CO3 2 minus, just our standard equilibrium expression. And then we plug those things in. We just get x times x, take the square root, and you get that x is equal to 5.08 times 10 to the minus 5th molar. And that's the solubility. The concentration of barium and the concentration of carbonate also happen to be that number, but whenever we solve for x, we get the solubility. All right, moving on. Comparing solubility. You've got two compounds. You want to know, I wonder which one of these is more soluble. And on first inspection, you might be like, hey, let me just go ahead and compare their K values. So if we take something like silver iodide, it's got a KSP value of 1.5 times 10 to the minus 16th. And if we take something like copper 1 iodide, it's got a KSP value of 5.0 times 10 to the minus 12th. And you say, which one of those is more soluble? And you're like, well, the KSP for copper 1 iodide is larger, and so it's probably more soluble. And you would be absolutely right, and that would be a great way of doing it. But let's do another way where it's not quite as obvious and see what we really have to do to make sure we're doing it properly. Let's compare copper 2 sulfide, which has a KSP of 8.5 times 10 to the minus 45th. 10 to the minus 45th. That's insanely low. It's just ridiculously low. That thing's not very soluble. Okay, and we're going to compare it to silver sulfide, but when we say silver sulfide, we need to make sure silver has a +1 charge, sulfur has a -2 charge, so we need 2 silvers to balance, right? Have to know those things. And that's 1.6 times 10 to the minus 49th. Whoa! And you think, okay, which one of these is more soluble? And you're like, hey, well, the copper 2 sulfide, it's got a KSP that's larger, right? 10 to the minus 45th is larger than 10 to the minus 49th. But is it more soluble? Well, it turns out you have to calculate that. If we were to write these guys out, copper sulfide goes to copper 2 plus and sulfur 2 minus. If I did my ice tables, I'd get an X and an X here. If I did my sulfide, I'd get 2 silvers and just the 1 sulfide, and I'd get 2X and X. And just like we did on the last slide, I'm not going to show all the steps there, right? On the copper sulfide, I'm going to take the square root. On the silver sulfide, because I've got that 2 there, I now have an x cubed. I've got 4x cubed, actually, on the right-hand side when I do all that math. And so I divide my KSP by 4, and I take the cube root. And here, when I do the solving, and I'm not doing it for you, I'm just going to give you the answer, x is 9.2 times 10 to the minus 23 molar. And here, x is 3.4 times 10 to the minus 17th molar. Now, both of these numbers are insanely small. I mean, think about 10 to the minus 23rd molar. Right? What's Avogadro's number? About 10 to the positive 23rd. That means if you have a mole of copper 1 sulfide in there, roughly 1 of them dissociates into water. It's crazy small. Okay, but look at our solubilities, right? X is always the solubility. 3.4 times 10 to the minus 17th is 6 orders of magnitude larger than 9.2 times 10 to the 23rd. And so even though silver sulfide had a smaller KSP, it is more soluble, because how we calculate solubility is by calculating X, not by comparing KSPs. It worked in this case because these were both the same. This was going to be X times X if we did it. This was going to be X times X if we did it. So you can directly compare KSPs when they fall apart into the same number of particles in the same way, right? It can't be that, one falls apart into 5 by doing 4 and 1, one falls apart into 5 by doing 2 and 3. That doesn't work. Then you'd actually have to do all the math. But if they each fall apart into 1 and 1, they each fall apart into 2 and 1, you don't have to worry about the math. Then you can compare KSPs directly. However, if they fall apart into different things or in different ways, then you have to actually do the calculation. Make the ice table. Find your x's, your 2x's, your 3x's, cube them, square them, whatever you need to do. Solve for x, and then compare those things, because those are the solubilities. So when comparing solubilities, do the work. Do the work to actually do it. Don't just say, this one has a higher KSP, it's more soluble, because that's not always true. Your turn. Which molecule here has the highest solubility? You're like, hey, I just picked the highest KSP, right? No, he said we couldn't do that. Let's look at each one of these. What does AgCl break apart to? Ag plus and Cl minus, that's X and X. AgOH, Ag plus OH minus, that's going to look like X and X. BaSO4, Ba2 plus and SO4 2 minus. Doesn't matter about those charges. The charges don't matter. It's breaking apart into 1 and 1, and so we get X and X. CaCO3 is going to break apart into Ca and CO3, and it's going to be X and X. So hey, look, they all break apart identically, so I can just compare KSP values. Which one has the largest KSP value? Silver hydroxide. And so silver hydroxide has the highest solubility in this list. So pretty good to do when you have things that break apart similarly. Just compare your KSPs. However, when that's not the case, what do you got to do? When it's not the case, you got to do the work. AgCl, we know is going to break apart. We've done that one a few times, so I'm just going to write the X and X. You take the square root of that, and you find that X is 1.3 times 10 to the minus fifth molar, right? That's our solubility. FeOH2, it's going to break apart, right, into 1 iron, 2 hydroxides. We got to square that, and then you find that X is 1.6 times 10 to the minus fifth. Right? So even though there's 4 orders of magnitude difference between those KSP values, their solubilities are almost identical. FeOH3, is going to break apart into 8 and 3x cubed. Right? So we actually have a x to the 4th here. We're going to have to take the 4th root in order to solve that one. When you take the 4th root of that, you get 4.5 times 10 to the minus 10th as your solubility. This should all be in molars. And then calcium is going to break apart into 1 calcium, 2 fluorides, and square. And I just did that middle column here with all my x's, right? That's just a kind of a summary of what's going on. In order to calculate that solubility column, I actually had to do that math. I had to take x times 3x cubed. It's 27x to the 4th is equal to 1.1 times 10 to the minus 36, and then divide by the 27, then take the 4th root. That's how I got all those numbers. But I'm shorthanding it here. Hopefully, if you're having questions, you can go back and see if you could reproduce my numbers. Here I get 2.1 times 10 to the minus 4th. So even though I've got a 10 to the minus 11th there as my KSP, I end up with that one having the highest solubility, and we get calcium fluoride having the highest solubility in that one. So in this section, we've defined kind of solubility as, hey, it's not 0 dissolving, it's some dissolving, sometimes really small, like 1 molecule in a mole, whoa, and sometimes bigger, right? 10 to the minus 4th molar. That's not unreasonable. We run across those kind of concentrations when we do experiments and things like that. Then we said, hey, how do we calculate the actual solubility? It's always X, no matter what the stoichiometry is. Then how do we compare solubilities and do the work, right? You got to make sure that you're breaking things apart into the right number of pieces, doing the math, and then comparing solubilities that way. All right, thanks so much for listening. Have a wonderful day.